I'll just pass it over.
Okay. Yeah, so I'm Dennis Staley. I'm a research scientist at the USGS Alaska Volcano Observatory, and I heard some comments that people were gathering about other presentations we've done, one most recently at the RCAC meeting. And if you remember, that was me. So I've spoken with a few of you in the past, most likely. But tonight I'm going to be mostly quiet and going to turn it over to Lauren, who's going to talk a lot about some of the recent analysis that's been done out in Berry Arm. So Lauren, go ahead and take it away.
Maybe turn it up as well, please.
Thanks. Yeah, I'll wait until you guys adjust levels in the room. Am I sounding okay?
Yep, you sound good.
Great. Okay. Yeah, I'm Lauren Schaefer. I am in Golden, Colorado, with the Landslide Hazards Program and the U.S. Geological Survey. Although I do most of my work in Alaska. So Dennis and I work together quite a lot, and I visit as often as possible. And I heard also a couple of you talking about Berry Arm as you walked in. Sounds like we could all share lots of stories about it. And I will be talking about that landslide because it was kind of the birth of this project that Dennis leads. But also I'm going to kind of go beyond Berry Arm and talk about, well, number one, like what we know now about Berry Arm after a couple of years of research. And then expanding beyond that, what we know about other landslides in the Prince William Sound and the work that still has to be done. So because I am remote, let's see, I'm going to use this little red guy to point out some things. All right, so the Alaska Landslide Project, which is the project that Dennis leads for the Landslide Hazards Program, how did it come to be? In 2020, people may have heard of Berry Arm. That might have been the first time it's come on your radar. There was an open letter that was published by a group of kind of concerned scientists and citizens that described this landslide after having seen it from a boat. And so here are a couple of news articles that really capture the attention of the public and also of Congress and the Alaska Congress. And in 2021, Congress then authorized the USGS to work in Prince William Sound with federal, state, and local partners. And so funding was allocated specifically to kind of start developing this Alaska Landslides project and the Landslide Hazards Program. And Dennis moved up to Alaska from Colorado. And that was kind of the birth of this project. And so those three bullet points were are the kind of three main characters of this project. So conduct data collection to support this landslide hazard assessment. And specifically when this was first authorized, we were focused very strongly on Berry Arm because of all the attention that was on it. But again, like I said, we've expanded since then. And then, provide recommendations for long-term surveillance strategy. This is, a challenging place to get to in general. It's isolated, it's boat and helicopter access only. Harsh conditions, as you all know, I heard it's snowing there. And kind of harsh conditions year-round, raining, snowing, lots of wind, tough place to put ground instrumentation. So what have we found out, in 3 years related to that? And then the third is to work with partners to develop an emergency early warning system because this landslide, as you might have noticed in that first picture, is partially situated now above those fjord waters. So if it would fail catastrophically, it could enter water and create a tsunami. So these were our three kind of main objectives. Probably don't need to show you all this location map. But just in case to orient, we are talking about Berry Arm and, Whittier, Valdez, Cordova highlighted. Obviously, Prince William Sound is a very large place. And we're concerned about landslide-generated tsunami because of the way that tsunami can propagate through the sound and impact areas much further from just the landslide itself. Okay, so here we have the 26 Glacier Cruise as a size comparison there in front of Berry Arm. Berry Arm is a really large landslide, which is part of the reason why there was so much initial concern, is still concern about it. It's several miles across and tall. It's really, this Glacier Cruise is tiny, it seems so tiny in front of it. It looks like an ant. It is a really massive landslide, and potentially has a lot of material that could fail into the water. So we are interested in understanding how and when it moves, why it moves, what would happen if it were to fail. And then I have to say, Dennis, again, has been leading this project. He's done an amazing job of developing partnerships in Alaska and beyond with people like the National Tsunami Warning Center, the Alaska Earthquake Center, and the Department of Geologic and Geophysical Surveys, the Alaska State Geologic Survey, to kind of put our forces together to be able to do the best that we can to understand this landslide and also to survey it. And then also, this group has been working on outreach and education, and also developing this kind of communication protocol. So if this thing is to fail, how do we communicate with each other to assure that the messaging gets out? So for some historical context, this red line here is kind of outlining the top of the landslide. And so you can see this image on the left in 1996 and on the right in 2017. Actually, it looks very similar now to what it looked like in 2017 in terms of glacier position. But you can see that in the last few decades, there's been really kind of this more rapid glacier retreat that we've seen. And previous study before we really became involved showed that with that rapid glacier retreat, the landslide also moved faster than its typical trends. So on the top, we see this line that's indicating landslide movement. And so an increase in slope means the landslide's moving faster. On the bottom, we see the glacier movement. And with an increase in glacier movement, we see a direct correlation with increase in landslide movement. And in more recent years, we can see this kind of leveling off. So the glacier slowed down, and also the landslide has slowed down. And spoiler alert, this is where kind of the rate that we're at today. So around a meter or two, so that's like 3 to 6-ish feet of movement within a season is typically what we're still seeing. So it's not, that is quite a bit of movement for a landslide still. So it is kind of concerning amounts of movement as landslide scientists, but certainly nowhere near what it was when that glacier was retreating from the base of the landslide. So what have we done? I put this link down here, and we can share things in the chat or with you after, or however we can communicate. But basically, this is showing the Berry Arm landslide and the location of all the instrumentation that we've put out at the landslide since 2021. And so this website is interactive. You can go through and click each of these points and learn about what instrument is there and what it's doing. But again, together with these partners listed here, we've installed meteorological stations, which are measuring rainfall and temperature and things like this, soil temperature. We've put out seismometers and infrasound, which is measuring acoustic noise. And so this picks up things like glacier movement, but it can also pick up things like if the landslide starts moving, if there's an increase in rockfall, or if there's landslide movement, we're hoping that that instrument can pick up that movement. We've also installed tide gauges, and National Tsunami Warning Center has installed tide gauges. And all of this information is being telemetered to these various groups at the bottom. And so some of this information is coming in real time, like those seismic stations, and you can actually look at that data online. So one of our colleagues at the USGS modeled what would would happen if this landslide were to fail in its entirety. And this is the resulting tsunami wave. So this is showing maximum wave height if that landslide were to fail. And this is assuming, that this landslide is pretty deep, like on the order of 200 meters deep, and not on the order of 500 million cubic meters in volume. So really very large landslide. I think something like it can fill the Empire State Building like around 100 times in terms of the amount of material that would fail. So immediately, I think I heard someone talking about Lituya Bay and kind of comparing the two. Immediately in Berry Arm near the landslide, there would be a 200-meter tsunami wave. So this is comparable, if not, I think bigger, Dennis. I can't quite remember, than that would happen at Lituya. In 10 to 15 minutes, that wave would propagate through to the south, and there would be about 5-meter high waves throughout this region. And as that wave kind of continues to propagate through the sound, all these areas in orange are seeing wave heights of 2 meters or less. In 20 minutes is when the wave would be offshore of Whittier, and it would be about 2 meters. And then in 2 hours, that wave will have propagated through the whole sound. And so this is, great information. It is a model, of course, but this gives us an idea of kind of the timing of a potential wave and also kind of the magnitude of that wave in different areas. And this model is being refined, with new information as we get it. So again, here is, there are, like I say, tsunami capable tide gauges that are being operated by National Tsunami Warning Center. And those are, you can actually see that data online. And that would be kind of our first indication. This is the warning system for a landslide generated tsunami would be this system that we have set up. And so this would be, this is where the USGS hands off. We're not here to provide a warning for this tsunami. This is really the National Tsunami Warning System. And so we have here kind of how they create those warnings or advisories or watches. But obviously with that other instrumentation that we have out, like our seismometers and our webcams and things like this, we would hope to have kind of more than one indication that this landslide has failed and a wave is currently propagating through the sound. So yeah, and this is a location. You can see kind of a station here, what it would look like if you were on a boat looking onshore. Okay, and so then with continued research, and so this, like what have we learned about this landslide? We've done a couple studies. One came out in a couple came out in 2023. Some new ones have come out in early 2024 to describe really what is this landslide doing? How is it moving? Because how it moves really matters to us as landslide scientists, because it tells us what its potential is to fail, how it will fail, whether it will fail slowly or quickly, and then what parts would fail. So is it going to fail in its entirety, or are just pieces going to fail? So all of this information is really good information for us, and also impacts how we end up modeling it in that wave. And so all the work that we've kind of done so far is kind of can be broken down into mapping components and then surveillance components. So that ground instrumentation that I pointed out, and then also using satellite data. Let's see. So just we can have like an open discussion and go into as many details as you all want at the end, but I just wanted to kind of synthesize 3 key takeaways without going like too far into the methods and those details. So the first key takeaway that we've noticed in our time of surveying this landslide is that it tends to move in the fall. So we are still unraveling what is exactly the triggering mechanism for this landslide to move, But we are seeing this continued pattern of this landslide moving in the later season, so late summer, fall, moving into winter. During the years that we've looked at it, there's been some really heavy rain around this time. We're also thinking about rain on snow. So there's the glacier that's been receding from the toe of this landslide complex, but there's also a glacier above it. The Cascade Glacier kind of runs above the landslide. And so we're interested or wondering kind of, how much water is infiltrating maybe the back of the landslide, as temperatures warm throughout the summer. And water starts moving into the landslide. Could it be coming from that glacier? So we think about that. We've been noticing, for example, in the fall that the springs on the landslide suddenly start to activate kind of more readily, and things like this. So again, this is something we're really still unraveling, but this is kind of a good indication for triggering mechanism, this kind of later season. But it's challenging, especially with these large bedrock landslides that have such a complex, potentially slip surface. They can be super deep, and it's just really hard to be able to figure out what's going on at depth. And I don't know, we can ask Dennis, but I don't think we're going to be drilling a hole into this landslide anytime soon. That would really be a great way to find out more information, but unfortunately, I'm pretty sure we're not going to be doing that on Forest Service land too. So we have to kind of make some assumptions and about what could potentially be happening at depth. So this graph, these are kind of 2 points on the landslide. These words right here are how we've mapped the landslide, and we split it into what we call kinematic elements. And so according to our mapping, each of these pieces of the landslide move slightly differently than the other one. So they all move a little bit differently. That's why there's kind of boundaries drawn here. And so this graph is just kind of breaking down when we see this point moving and when we see this point moving in both LiDAR and a satellite technique in SAR. And so this is obviously very small. I can hardly see it on even my screen, but this just shows there's an increase in movement in this year and also in this year towards the end of the season. So we're seeing this pattern kind of continuously. This was a little bit of an anomalous year in 2021, which is interesting for us, but not super surprising in the landslide world that something won't behave the way that we think it will. So that's actually quite an important data point for us, because it could have been quite rainy that year, but it still didn't cause the landslide to move. So, this is just kind of sleuthing and trying to get at those triggering mechanisms for movement. Okay, key takeaway 2 is that portions of the landslide are capable of moving by themselves. And sometimes we see that like one kinematic element will move and none of the other ones will. And then we see times in a year where all of the landslide moves, or one element will kind of start this trickle effect, and one element will trigger the other element, will trigger the other element to move, which kind of, in a nutshell, describes how complex these landslides are. They don't always do the same thing. So this is a technique, again, called INSAR, that uses radar data from satellites. So these are maps of kind of how the ground is moving. So anything that kind of looks like this stripy fringe pattern, that indicates movement of the landslide. And anything that looks speckled is noise in the data. There are lots of reasons why there's noise in data like this. It could be that there's snow, or the surface is too active. Something is just disrupting the satellite signal. So what this is showing, and this is 2 different years moving to the right here. So on the top, we have 2020, and on the bottom, we have 2022. So 2 periods when we saw this landslide move quite a bit. And we can see that movement really starts just in one kinematic element. It moves by itself for a while, and then it starts to trigger the next one over. And then finally, the whole landslide starts moving. And this is quite cool to see this happen kind of 2 years in a row, or not in a row, but in 2 different years. Again, it just gives us more insights into how this thing moves and might help us kind of predict how it would move in the future. So then the final takeaway is that we are finding that the landslide movement is influenced by the glacier. I know this doesn't sound like anything that new, considering I showed you that graph that correlated landslide movement to glacier movement, but the glacier has really slowed down in recent years, and we're still seeing impacts to this landslide, even with the glacier, not moving as rapidly. So here in this picture, this is a top-down image. Again, we have this landslide outlined here, all those different kinematic elements, and the glacier outlined here. And we can see that the landslide was moving just above the glacier in this little kind of triangular area. And when we went into the field and took pictures, we could see these kind of arcuate crevasses in the glacier right in front of this area that was moving. So glaciers always moving. There was obviously movement happening at the glacier in this point, and it was impacting the landslide. You can also see a slight curvature to this glacier toe, which indicates to us that the kind of downward movement of the landsliding is pushing that glacier. And so, buttressing is a big question in this kind of landslide glacier world. Obviously, we have evidence that dates this landslide back to 1937, I believe, if not earlier. And the glacier was fully below the toe of this landslide. So this landslide has been moving even with the glacier fully there. But obviously, the removal of this glacier did impact the way that this landslide can move. It still looks like it's impacting this landslide. And I think, thinking forward, we're expecting the landslide to continue to move differently as this glacier continues to retreat from the toe. And I think, kind of the most obvious consequence is that in previous decades, if this landslide were to have failed, it would have failed primarily onto ice. And now it has the potential to fail into water. And this obviously has big impacts for any potential tsunami. Okay, so a lot of this information that we find is communicated onto the DGGS website that is specific for the Barrier Arm landslide and tsunami hazard. Again, Dennis, if you want to throw this into the chat too, this link to this website, we communicate, what we're doing, if we're putting out new instrumentation, if our instrumentation is working, if we see this thing moving either in our ground instrumentation or satellites. We put this all on this website. And there's also kind of the status alert that goes out. That's organized by DGGS and the National Tsunami Warning Center with assistance from the USGS. And you can also see this kind of clip of like a tweet, for example, of how we're disseminating information. So we interrupt our volcano content for this update on the Barrier Arm landslide and tsunami. So this is even on people's radars who normally wouldn't be paying attention to these things. But to be fair, this landslide is about as large as some of those that we see on volcanoes. So it's caught the attention of many scientists. We also, do outreach with school groups and other organizations. We have videos online describing what we're doing. Whittier, the city of Whittier has also recently been designated as a tsunami ready city. That's a designation by the weather, National Weather Service. Sorry, so many acronyms. It's hard to keep them all track. But that's a real win for us. in this whole project and this whole experience is, getting the word out, making sure that people are aware of the hazard and know what to do in the event that it would actually fail. So I'm going to expand now beyond barrier arm, but I don't know if we can pause for questions or just keep trucking, and you can learn about all of these other landslides we found before asking questions. Up to you all.
Yeah, go ahead.
If there's an indication of movement, would that be on the weather forecast, National Weather Service notice to mariners? Because, there's a whole fishing fleet that's right there, up close.
Yeah, Dennis, do you want to take that?
Yeah, I can take that one. So we see small amounts of movement pretty much throughout the entire season that we're able to see the landslide with our instruments. So from May through October, there are localized areas where you do have small amounts of movement. So that's a fairly standard common thing that we see out there. Once that exceeds a certain rate of about 50 millimeters per day over a certain size of the landslide, at that point, it really attracts our attention as scientists. And as when we see that, the first thing we do is we contact the National Tsunami Warning Center and say, hey, we're seeing evidence of broader instability and increase in deformation rates. And we also contact the Coast Guard. And so they have different sets of messages that they will send out through their automated system, through their the written bulletin to mariners. And there's one other radio product that I forget the acronym of, but they do change their message as we see increases in the spatial extent over which the deformation rate is increasing. So yes, they do change their message.
Any other questions? Yeah.
Does that company that there was a picture with them for scale still operate in that area, knowing maybe the risk, or would they go by the same assumption that they would hear about instability and not go that far in there?
I can actually speak to that because I spoke to the boat captain pretty recently. So no, they've actually changed their crews to not idle in Barry Arm anymore. So they still operate a 26 glacier cruise, but it's a different set of glaciers now than those in Barry Arm. So I guess that's kind of another indication to us that the messaging has been heard, is that, they're not comfortable idling there for long periods of time like they used to, knowing that landslide is there. So that being said, I think, there's always kind of risk fatigue, right? There's also, I would say, kind of, we're still learning how this landslide operates. And so at first everyone was worried. No one really knew what was going on because there was no instrumentation in the ground. Well, now that we're kind of developing this repertoire of information, those behaviors might change in the future, and for a good reason, right? We might determine that the risk is different than what we first assumed. So I think it's kind of an ongoing process. But yeah, I can tell you that for now, they're not idling in Barry Arm.
Is there a question?
Yeah, my question is about the volume of material and the depths that are there. Is there enough material, if the whole thing were to go, would it close off the arm?
Yes, I don't have like the numbers in front of me. I can't remember exactly how far that material travels, but certainly the amount of material entering the water in front of the landslide, the volume of that water body is smaller than the landslide itself. It's actually quite shallow in that area. I don't know, Dennis, if you want to talk about that at all, but definitely it would fill that area directly in front of it. And the run up on the opposite side of the bank would be, I think it's about 500 meters. So it's a really kind of narrow and steep area. So that landslide would fill, and then run up on the opposite bank for 500 meters, in addition to then kind of spilling out into the, and kind of flowing down the fjord.
So if that happened, would the potential be for a lake to fall, to form behind it? You know, and then you'd have a situation like with the Hubbard Glacier making that, occasional flooding at unexpected times.
Yeah, that would be a pretty interesting scenario. I guess we haven't really thought too much about what the post-failure topography and hydrology would be like in that valley, but that's a really great question. I think there's a significant amount of water that comes out of the toe of the Berry Glacier, and so if you were to introduce a lot of sediment to the area just below, just beyond the terminus of the glacier, or wherever that terminus is after the landslide, then yeah, I think there could be potential for damming of lakes there. But I think that's kind of a really unknown question. So the water depth itself is, I want to say it's like 70 meters or so, so a little under 200 feet just at the toe of the Berry Arm landslide. And then it gets up to about 200 meters as you get further out into Berry Arm. And so the volume of the landslide itself is far greater than the volume of water that's just immediately below the landslide. So the material would propagate out probably below the island and fill in that entire stretch between the glacier and the island. Yeah, and that's a lot of material that could have potential to be reworked by the stream channel processes, and who knows, potentially cause a small lake up there. Lots of lakes in the sound and similar types of valley configurations. Great question.
Any other questions? No?
I do.
Oh, one more. Go ahead.
Have you figured out how an earthquake and what magnitude would affect it if it were to hit, in the region?
Another very good question and an astute one, because we're susceptible to really big earthquakes in Alaska. The answer right now is no. We don't know what size of earthquake would shake it loose. We do know that the landslide made it through the 1964 earthquake, but that really doesn't predict anything about what could potentially happen in the future. And Lauren knows a lot more about that than I do, so I'll defer to her to comment on how landslide stability evolves over time and material properties change as things forward. But we do have a colleague going to Japan next month to run some laboratory tests where he basically takes some samples that we collected at the landslide that we think are representative of the material that's actually sliding, and he squishes them and he twists them. And as he applies stress to that sample, you can see how the material behaves under that load, and you can then make some assumptions about what the forces are that are needed to where that material loses strength very rapidly, and that from that you can infer how it would behave during a strong shaking event. But we've only run one set of tests so far. They're kind of time consuming, and not many places in the world where you can do that. But we've got one round of tests that were done last year and another that's going to be done in a month to confirm or refute what we saw last year. So hopefully we'll have some more information on that here in the coming months. Lauren, do you want to comment on landslide behavior from prior earthquakes and what that means?
Yeah, it's a question that's on our mind a lot, and for these kind of other landslides that we're finding through the sound. I guess so 2 comments. One is that in 64, obviously the conditions at this landslide were much different than they are today. There was a lot more ice sitting in front of this landslide. And we have evidence now, again, that links kind of glacier and landslide interaction. So we have a lot more landslide exposed to the water. So that's obviously one big difference between then and now. And yeah, I mean, this rock, that composes the Chugach Mountains is called Flysch, the Chugach Flysch. And it's really kind of honestly crappy rock. It's constantly, it's been through a lot. It's been through a lot of like glaciations. It's really fractured really heavily. There's lots of places that water can infiltrate through this rock mass and just kind of constantly degrade the quality of the rock, which just over time kind of promotes failure, not to mention we're dealing with super steep slopes and again, those glacier dynamics. So yeah, I mean, things have changed a lot since that last large earthquake. Like Dennis said, it's not really indicative of what would happen if something similar would happen now. And obviously there were a lot of landslides that failed in this region in '64. So, I mean, that's kind of the major piece of evidence we have to point to. Another thing to think about, and not certainly we don't like, or try not to exaggerate the hazard, right? But these landslides are kind of, they're already failing, they're already moving. So a mass that is moving, we're obviously concerned about what an earthquake would do. It could do nothing, or it could be the hair that broke the camel's back, So I think we're kind of still investigating that. And there's modeling that can be done with, some assumptions. So it's just trying to make those assumptions as kind of educated as possible. Things like the volume, we're really quite uncertain with again. But maybe just trying to keep track of time, maybe we'll just go through kind of how we've expanded beyond barrier arm, and then we might have a little more time at the end for some more questions. Just want to introduce you to more landslides that we've found throughout the Prince William Sound. Again, not to sound the alarm, but it is good information to have, and new information, very new information. So this just came out in January of this year. And the purpose of this study was, asking, okay, Barry Arm is a very large, potentially tsunamigenic landslide, but this is a really large area. There are similar conditions elsewhere in the Sound. So where are other landslides? And also, are they moving? And so to do this, again, we use radar techniques to cover such a large area because it's just not possible to instrument every slope in every place throughout the Sound. Dennis just nodded to that one. It's been very challenging getting all the instrumentation at Barry Arm alone, let alone at other slopes. So again, that's not feasible or plausible. So we turn to satellite techniques. And again, we're using satellite techniques that can tell us how the ground is moving. And we use a slightly different technique than kind of some of the images I've already showed you, called persistent scatterer in SAR. And so what this allows us to do is to look at many years of data, so very large timeframes, and then to be able to measure very small movements. So things as small as millimeters per year of movement. And what this allows us to do is to pick up kind of these slow bedrock landslides, which is what Barry Arm is what we would expect elsewhere. So with this goal in mind and using this method and conducting this survey across all of the Sound, we did find 43 landslides that are actively moving. And by actively, I mean there's evidence of them moving between 2016 and 2022. And that's just, those years were done just because it's a limit of the satellite data availability. And so on this map, anything that has kind of a white, a name that has kind of a white background and a leader line is pointing to one of these moving landslides. again, I'm going to emphasize this now and then again later. There are limitations to this method. It can't measure anything that has vegetation on it. So any slope that has vegetation is basically out. Any slope that has snow on it is basically out. Any really active slope, so things with lots of rockfall, is out. So it cannot measure everything. And you'll see this more obviously when we zoom in on an example later. But that being said, this did pick up quite a lot of landslides in this region. So then the next question, just like Barry Arm, we're wondering, could these landslides, if they were to fail, could they generate a tsunami? And so instead of doing that kind of computationally intensive modeling that we showed earlier of the wave propagation, we did a more simple kind of geometric analysis of an assumed volume of the landslide and then the travel distance to the nearest water body and assumptions about the landslide's ability to move to that water body. So using this method, now everything highlighted in blue, we determined to be a landslide that has the potential to generate a tsunami. And so obviously Barry Arm, the one that we all know now, is one of those landslides. This is 11 now. Another one in Barry Arm, actually, there's several in Yale, several clustered around Whittier, and then a couple in a few other locations, but it is kind of clustered in this western portion of Prince William Sound, which might just be a limitation of the method. We're still kind of looking through that. But we do see kind of a clustering in those regions. So let's zoom in on what this data actually looks like. This is a scene. So we're looking at Whittier, kind of down Passage Canal. This is Maynard Mountain, and we're calling this Maynard Mountain landslide, and outlined here in red, kind of sitting above the city of Whittier, above kind of where the airport is, if you're familiar with that. This is that tunnel that goes to Whittier and then the road that goes into Whittier. So when we're looking at the data, anything that is kind of like a colored dot means that it is an area where we could get a piece of information. So whether or not the ground is moving. If the dot is green, it means it's not moving. And if the dots are blue or red, it means the ground is moving, or yellow. So you can see here, this kind of highlights the limitations of the method. So anything that has vegetation on it we're not picking up. Things that have snow, we're not picking up. So this area, these landslides in this region, the reason that this method works so well is because we have these large bedrock, so just rock surface landslides. So that's why this works so well. But you can see that there is movement of this landslide above Whittier. And then I probably don't have to describe, the potential impacts if this thing were to fail. I'm sure you all can imagine. So that not only would it, cause the city of Whittier to be isolated and fail onto infrastructure, but it would also very likely enter Passage Canal and create a tsunami as well. Another landslide that I want to highlight is one in Yale Arm. So this is Barry Arm again, and then we're up here in Yale on kind of that south, well, I guess it's a north-facing slope, but on the south side of Yale Arm. I have it highlighted here again in red. This one is kind of akin to Barry Arm in that we have this glacier that now has basically retreated fully from the toe of this landslide. And so it's now sitting basically totally above the water. Again, it's a really large landslide. We can compare it to Barry Arm here, now with this dotted line. So if Barry Arm, we're assuming is 550 million cubic meters, using that same method to get that volume, Yale would be nearly twice as large. So that line is showing it's 1.5 miles wide, which sometimes I like to just think about like how long it would take me to even walk 1.5 miles. These are really large landslides. And obviously, you know, again, this data is showing that this thing is moving, but we are missing a lot of information on the landslide. So we're currently, you know, trying to learn more about these landslides, how they're moving, if we can use other information like LiDAR. I can see Katrina's online. She's our LiDAR, I don't even know, queen. She's been amazing at processing and helping us interpret LiDAR for this project. And so that really helps fill in some of the gaps that the satellite data cannot see. And obviously LiDAR is a really good tool for very in-depth mapping. So we've expanded our LiDAR acquisition to encompass a lot of these now areas of interest. So some of these kind of landslides, especially the ones that have the potential to create tsunami, we've expanded our LiDAR footprints. So we have now a lot more information that we're just have recently gotten that LiDAR. And so we're going through that and trying to understand, again, structures, kinematics, movement behavior, all of these things that give us an indication of the hazard and the risk. So just for example, this is kind of my last slide. This is the SAR inventory. We're just looking at the western portion of Prince William Sound. SAR was able to pick up 26 moving landslides in this region. But then we've also, our team has gone through and just looked at, you know, just regular, basically photos of the earth to look for landslide features like cracks and headscarps and rockfall and things like this. And they picked up 61 in this region, which are highlighted now in yellow. So if you overlap those two methods, there was 14 that were in common, making a total of 87. So this highlights a couple of things. One is that you really need more than one method to look at these regions. And two, there's probably more landslides out there than we know of. And three, this is more than just kind of a barrier arm problem. There's obviously a lot of landslides. We obviously cannot instrument them all. So there's kind of a lot of work that we're going through right now to identify those that are the most concerning, learning about them, and kind of deciding with our partners how to address these hazards moving forward into the future. And this just little inset just shows even when you have a landslide that two methods have picked up, but you draw the outline of your landslide using two different methods, it's going to look different. So there's a lot of work to still be done to kind of figure out what even the actual size of some of these landslides are. So key takeaways. Again, Dennis has done an amazing job managing this project, forming these interagency partnerships, which has permitted us to characterize this landslide. And I think one of the biggest highlights, is that there are now tsunami-capable tide gauges that are producing real-time data available in the sound, and that message is being communicated. And Whittier is a tsunami-capable city, or tsunami-ready city. We have this very new information that we have more landslides to worry about. And so we are doing our due diligence of finding out more about these landslides, just like at Barry Arm, because not all of these landslides should be treated as equal. We're not here to tell everyone to never go into the sound again. Quite the opposite. We think the hazard and risk associated with each of these landslides is different, and it's going to evolve with the more information we get. So we were just talking about that with the glacier crews and whether they enter Barry Arm and what they're thinking about in the future. And just, a reminder that different data produces different inventories. We're trying to get the best data we can, and every time we get new data, we really learn something new. So again, I think that kind of wraps it up, but Dennis and I can stick around for any questions, or please feel free to contact us if you have any questions outside of tonight.
All right. Thank you so much, Lauren. That was a great talk. Does anybody have any questions? Yeah, go ahead.
Well, it's a question, but it's kind of based upon long-term observations. We've had, it seems an increase in the number and the significance of landslides that have occurred in Alaska in recent times. The Tia Bay is certainly a big one. It seems like there's been several significant landslides in the Mount Fairweather area. More recently, locally, Sitka comes to mind, but I don't know exactly if that's indeed the case, but certainly Haines. I know Haines, up by the border, up the 36-mile area, they've had a huge mudslide, a reoccurrence that's happened there. Haines itself, quite close to town, they had another mudslide, and most recently in Wrangell, they've had a mudslide that caused several fatalities. And it just seems to me that these are either we're becoming more aware of them or they're happening more frequently. But be it landslides, mudslides, or avalanches, it doesn't take a whole lot to ruin your whole day. Where we sit right here, right now, there is a fault line that runs right through the side yard. We have a USGS has a seismometer just up on the ski hill here up to our right. But anyways, if you ever had a chance to come to Cordova, June would be a good time to come, and maybe we can get together and go up on the ski hill and wave our arms around, jump up and down, and say, well, what about this?
That sounds awesome. I'm just going to touch on the occurrence, like the observation that you're making about, there seems like there's more landslides happening, and I'll speak for kind of these type of landslides that are the bedrock landslides, and then I'll switch it over to Dennis, who can talk about the ones in Southeast Alaska. But yes, and we actually, our other colleagues who have worked a lot in Glacier Bay have data that shows that there is an increase in rock avalanches in recent decades. And they attribute this to climate changes, glacier changes, permafrost changes, and actually just changes in weather patterns too, which is kind of a major impact for Southeast Alaska as well. So I think, yes, that is the case. In Prince William Sound, that direct correlation has yet to be made, but it wouldn't surprise me at all to see that pattern happening in Prince William Sound as well, kind of similar to Glacier Bay. Dennis, do you want to comment on Southeast?
Yeah, sure. So the landslides in Southeast are a different flavor than what Lauren's been showing here, but they are generally produced during periods of either prolonged rainfall or intense rainfall or a combination of the two. So prolonged rainfall could be large seasonal accumulations or things as much as a 3-hour burst of rain, a lot of rain over a fairly short period of time. And so I think that, yes, we are more aware of these now. I think there's more people around to get eyes on them, and unfortunately be in their way in a lot of cases. And that's a true tragedy when that happens. So we do have the recent events in Sitka and Haines, and now just this past winter in Wrangell. So we are definitely more aware. I think there's a greater population now, and so there's a higher potential for that to impact either people or the infrastructure that support the people in these areas. So there's definitely a greater awareness. Now, whether or not there's a link, an increase in the frequency or magnitude of these events with climate change, I think that's still an open question. What we do know is that if you see more rain over the period of the rainy season, or you see more intense rain, then that increases the likelihood that you could have these shallow landslides that could be potentially fatal and tragic. If climate were to change in such a way that increased the length of the rainy season, the total amount of rain in the rainy season, or the intensity of rain during that rainy season, then you would anticipate that you'd see a corresponding increase in the frequency and potentially the magnitude of shallow landslides in Southeast Alaska. So that's one of the longer term goals of all the different landslide scientists that are working in Southeast. That includes USGS, DGGS, lots of academic researchers. Your partner science center down in Sitka Sound has a large effort devoted to better understanding landslide hazards. So that'll be a long-term focus for sure. But right now, I think that we have to lay the foundation for doing that analysis, and that's just to characterize where we're seeing landslides, when we're seeing landslides, and then to do our best to reconstruct when landslides have occurred in the past too. And that's kind of a hard thing. Recovery happens very quick down there, so landslide scars get revegetated fairly quickly, makes them difficult to see. But one piece of technology that Lauren mentioned earlier in her talk is LiDAR. And LiDAR can really reveal what's happening beneath the canopy. And so 22 or 23 communities in Southeast now are either have been collected or will soon be collected, have very high resolution topography that the laser will penetrate that canopy. So we'll learn a lot more about where landslides have occurred in the past. And then we can use that information to do some susceptibility modeling, but also to better understand the triggering mechanisms and play some what if games with different climate scenarios to see what might happen in the future. But again, all of those are sort of long-term research goals, and we'll see where we end up and if we can clearly quantify that link between climate change and landslide occurrence.
Yeah, go ahead.
On your mapping of Whittier that you showed and that potential and that movement right there, was that mapping and data available in time for the cruise ship companies to make their decision of putting 2 cruise ship docks in that upper right corner of Passage Canal and building a cruise ship theme park right at the base, almost at the base of where that landslide is moving?
The construction commenced before these data were available.
Yeah. I just wonder what hopefully they're on your mailing list so they're aware of it. It'd be a real event.
The mailing list, yeah.
So what's the smallest landslide that you guys can map?
With that radar technique.
Yeah, with EEO, you had 2 different techniques. So
Yeah.
how small do you go?
Mm-hmm. Yeah. So the radar technique, those like this on the ground pixels are about 20 meters. It's kind of the upper edge. You can get very high resolution stuff, which is what we're using at Berry Arm, which is 2 meters or 6 feet. Confidently, there's a lot of noise in these scenes because the ground can move for lots of reasons, melting ice, things like that. I think we had put a lower bound on confidence for size that it had to be 50,000 cubic meters, was kind of the aerial extent that we felt confident saying, yes, this is enough moving pixels. There are 50,000 cubic meters worth of moving pixels. We're pretty confident. We then actually looked at additional data to verify, and in addition to this area being an area of moving pixels, we also see in imagery evidence of landslide features. So things like fractures, rock fall, scarps, things like that. So those two things combined kind of gave us the confidence to say, yes, this is a landslide versus something like ice melting, which can cover a pretty big area too. So that's kind of on that end. I don't know, LiDAR, Dennis, I don't know if you want to comment on that. That's such high resolution.
Yeah, the LiDAR, and I don't know, Katrine's online, but maybe she wants to stay semi-anonymous. But we've mentioned her name a couple times now. But you know, the LiDAR that's been flown is the resolution that's anywhere to 10 or 20 centimeters on up to a little bit over a meter probably, and it takes several pixels for you to really be able to detect anything. But our takeaway for most of the places that we've mapped in Alaska is that we discover tens, dozens, hundreds, thousands of new landslides every time we train our sites at a new slope. And those can be historic landslides where you see the evidence of past failure. You can see evidence of small amounts of deformation that probably aren't really a hazard, but they're interesting scientifically as to why they're there. And then you do see these larger landslides that are both scientifically interesting and of interest from a hazard perspective. So I don't think there's any real minimum size of landslide that we necessarily concern ourselves with. It's more on where that landslide is and how big is it relative to, or how far would it travel relative to where people are or where water is. That's our primary focus at this point. And not necessarily the total number of landslides that are out there. It's just identifying those that are of the highest hazard.
I was trying to do a quick Google of what 50,000 square meters actually means. Like what, if you can envision that. But I'm only finding really a polo field is 50,000 square meters. Anyone knows what a polo field looks like? Kind of. Anyways, it's like a pretty decent size, but certainly nowhere near like the size of Darien, for example.
Yeah, go ahead.
What is it? You said Whittier's a tsunami ready city. What's that mean?
Yeah, that's something that I'll do my best not to mix it up, but I can't promise that I'll get it entirely correct. So I think that there's been a thorough characterization of what the likely inundation areas are. So there's maps of using historical information from the '64 earthquake and other events, as well as some modeling. They now have a evacuation zone. So there's a route where you can take to get to safety and a clear demarcation of above this line, you're safe, given all of what we know about tsunami inundation in the town. There's also informational campaigns that happen that are associated with it. I think there's an annual event in Whittier to remind people of tsunami hazards and what to do in the event of an earthquake or the receipt of a tsunami warning. And there's also the infrastructure within town, like the siren, to be able to support that warning going out and being broadcast publicly. So I think those are the critical components, but NTWC would have or NOAA or the weather service would have the definitive word on what the criteria are to get that designation.
Yeah, go ahead.
Have they looked at Shepherd Point lately?
I'm not sure where Shepherd Point is.
It's up the head of the bay here out of Cordova.
Okay, so we have just started to focus our sites on the landslide end on Cordova. We had a team in town last year who we did some mapping of the geologic structure and lithology and some of the geologic properties that may make certain areas more conducive to landslides than others. So we had a team that started in Valdez and worked their way on over to Cordova last summer. I know that DGGS and FEMA are partnered for a snow avalanche hazard and landslide hazard study where LiDAR has been collected for pretty much all of the terrain that drains down into Cordova as well as into some of the adjacent watersheds. And there will be mapping of landslide hazards in that area. And we are also doing our optical inventory in and around Cordova as well. So while most of our attention over the past couple of years has been focused on northwestern Prince William Sound, largely because of Barry Arm and those other really large landslides that Lauren pointed out in College Fjord and Yale Arm. But yeah, we're definitely focusing more on Cordova starting this year and moving forward.
Mm-hmm.
When would we see, would that be like a year or so, or information?
It's hard to make promises for when publications will come out. USGS is a science agency where we take our peer review process pretty seriously. So we don't want to release things before they've been thoroughly checked and vetted and gone through the review process. And that can be lengthier than we'd all like it to be for the public and for the scientists that are trying to push it through the review process. But we are well along the way for the optical mapping that's been done. Lauren's radar analysis did cover Cordova.
Mm-hmm.
We just didn't see any of these large slow-moving landslides there. There's a few other types of analysis that we'll be doing in the area. But that's good. The optical inventory will probably be coming out in the next several months. I don't know what the other study that's going on with the state and FEMA and the time frame on that analysis. I don't know what that is.
Yeah, and I'll just add that just because I can't see it in this radar imagery doesn't mean it doesn't exist, which is why we're doing the optical mapping and other, applying other methods. Nothing will ever give us 100%, but we're trying to get better than just like a one method approach, because we've definitely seen from other areas that it's really important to get as complete an inventory as possible.
Yeah, that's a really good point, Lauren. We had some colleagues who were doing similar work in Glacier Bay, and I forget the exact numbers. I should have these committed to memory, but I don't. But they used the combination of the radar method that Lauren showed here with LiDAR, with the optical mapping, and each method contributed a third of the total number of landslides that were identified in the region. So it's not necessarily a single tool that's important, it's the combination of all of the tools that paint the more complete picture of the landslide hazards in that region.
Well, great. Thank you so much for answering our questions. If anyone else has any further questions, you can get in contact with me and I can put you in contact with them, or their emails are right on the screen. But thank you again, Dennis and Lauren. That was really great.
Thank you.
Yeah, it was a pleasure. Thank you.
And thanks to Lauren for staying up so late. 10 o'clock.
Yeah, it's my bedtime. Thanks, everyone. Bye.
Good night, everybody.
So we left that paperwork under my door. I'm starting to fill it out, and then it was the question left, and then I ran into the education. So gave me
Yeah, immediately.
Oh, yes.
Yeah. And then what they're building on can just be. Oh, yeah, 60. That'll last today. That's why we see more of them. Glad you get out and we have more people.